created an entangled state. What does it mean? Let me draw the complete quantum diagram in one go because I split it up into two parts. So what I'm doing is I input get 0, I have a Hadamard gate. So at this location I have created this state, right? Now why do I draw these fuzzy lines here? Because I'm not measuring it, I'm just writing what I think the state should be. Zero. Alright, so this is the state over here. Then I keep going on with these qubits and then I apply the circuit over there, which is the Hadamard gate, which is just the controlled NOT gate, okay, and the state that I obtain here is the state that I've written over there, 1 over under root 2 Now this state is an example of an entangled state. This state harbors entanglement within it. This particular kind of state is also called a Bell state. Bell was a scientist, John Bell. This is one example of a Bell state. It is entangled. Now what does that mean? First of all, something very mathematical. If you look at this state here, I can write this in this form. Now this form is something is quite illuminating because this form has big brackets around the first qubit and then follows the second qubit. So the state of the first qubit is written independently from the second qubit. Agreed? So this state is factorizable into what's happening at the first qubit and the second qubit. It can be the first qubit and the second qubit can be factored out. They can be separated. Right? So I can factorize this state into what's happening at the first qubit, what's happening at the second qubit. My measurements are also over here, they are factorizable or separable. What's happening at the first qubit is independent of the second qubit. What outcome I get at the second qubit does not affect what happens on the measurement outcomes of the first qubit. So I am living in two independent universes. One is this universe, it has nothing to do with this universe. The two realms are separable, they are distinct. And my outcomes here do not affect the outcomes here. I have a totally random output, classically random output like a coin toss. And I have a definite output here and the two events are separate. Alright? I can also have okay, fine. However, just by looking at this state, is it factorizable into the first qubit and the second qubit? Can I write this big state as the first qubit with the second qubit? Can I do that for this state? I can't do that. No matter what I do, it's impossible to write it as one big bracket for the first qubit and another big bracket for the second qubit. I cannot factorize this state into two independent qubits. No matter what you do, no matter how hard you try, you can't do that. Okay? So this is an example of an entangled state. But what does it mean as far as the measurement scenario is concerned? That's baffling. Now what I would like to do, I would like to have measurement devices on this qubit and a measurement device on this qubit channel 0, channel 1, channel 0, channel 1, counters or detectors here, D1, D2, D3, all right. Now let's see what's happening. Suppose I forget about, so these are two observers. Now it's conventional to call one of the parties in this experiment in any quantum setting Alice, and the other party is called Bob. Okay, so there are two parties in the experiment, Alice and Bob. So Alice is taking a measurement on the first qubit and Bob on the second qubit. Okay? Now Alice and Bob don't talk to one another. Okay? Now Alice makes a measurement. What's the probability that G1 clicks for her? 50% of the times D1 clicks, because first qubit is 0 with 1 over root 2, half. And what's the probability that D2 clicks? 1/2. And it's a totally random event. Totally random. Now, forget about Alice. Let's talk about Bob. Bob has a 50% probability that D3 clicks because he has a 0 with an under root 1 over root 2 and a 50% probability that this detector clicks. So both Alice and Bob are seeing totally random affairs. For them, the affairs are totally random. Now suppose that this particular state, these two qubits, were created on planet Earth. So there are two qubits. So here the qubits are on planet, living on planet Earth, and Alice decides she would like to take one of these qubits, particles, far away onto another planet. Okay? Suppose she goes to Pluto. Still it's a planet. But now Alice is on Pluto and Alice has a measurement device. She makes the measurements and Bob makes his measurements. And there are many copies. So one measurement is not enough in order to test probability. So you need a lot. So if you just have a single coin toss, you can't tell whether it's a fair or a biased coin. You need to have multiple runs. So many copies are available. And Alice takes her measurements, writes down her results on a piece of paper, and she moves back to Earth. Now the two qubits are totally separated out in space by hundreds of light years. Okay? Now they come back and they look at their readings. They compare their results. Alice thinks she has a totally random event, a random output, either D1 clicks or D2 clicks. She has a totally random string. So her string, suppose her string is, if she gets 0 here, she puts a 0. If she gets this detector click, she puts a 1. Suppose Alice's string is 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, so on. Suppose this is Alice's string. And Bob has a string as well of his outputs, 0, 1, 0, 1. And when Bob shows his string to Alice and they compare notes, Bob's string will exactly match Alice's string. Even though both of these are random events. What's happening here is that this Alice and Bob can be separated out in space, geographically separated. We talk about geography when you're on the planet Earth, but these are exactly celestially separated in the cosmos. They could be far, far apart, and they make measurements and they get totally random outputs. But when they compare their results, or Bob doesn't have to come back to planet Earth, she can make a phone call. Now, when they compare their results, their random strings, they totally match with one another. Because what's happening is that once both Alice and Bob make a measurement, this state collapses. It collapses into ket 0, 0 with a probability of 1/2, and into state 1, 1 with a probability of 1/2. So if she measures 0, Bob also measures 0, but they don't know what they're measuring. They don't know the measurement outcomes until they've met. And Alice on her own keeps on thinking that she has a totally random affair going on. Bob on his own thinks he has a totally random affair going on. So the parts are random, but the whole is not random. The whole is perfectly correlated. So this is an example of entanglement. These objects could be separated out in space, far, far apart, but still there is perfect correlation. Now there are more examples of entangled states. Let me finish, please. Alright, now I have this quantum circuit. On the first qubit, I apply a logic gate, quantum logic gate, which is just a NOT gate. So the state is of course separable here. I know what the state of the first qubit is, and I know what the state of the second qubit is. Here, if I give you this state, and I ask you the question, what's the state of the first qubit? Can you give me an answer? Looking at this state, I ask you, what's the state of the first qubit? Can you give me an answer? You cannot give me an answer because I cannot separate out what's going on the first qubit with what's going on in the second qubit. They're entangled. They are in unison with one another. They are conjoined with one another. They are one at the same thing. They are the same. They're just the same. Amir Khusro said, "Man tu shudam tu man shudi." I am you and you am I. They're just the same. Okay? And they can't be separated. Now this state is separable over here. Now I do a NOT gate on the first qubit. I would like to write this state over here. First question is, before writing the state, would the state be separable over here? Yes, because I know what the first qubit is. It's ket 1. The second qubit is still 0. So I know what the first qubit is, I know what the second qubit is. Now I apply a Hadamard gate. I want to find out what the state here is. And the Hadamard gate is only on the first qubit. Will the state be separable here? Yes. Still it's going to be separable because the two qubits do not bridge across one another. They don't talk to one another. Okay? So the state here is going to be 0 minus 1 for the first qubit, and nothing happens to the second qubit, so it's still going to be 0. Now I apply the control NOT gate. Now, if I apply this control NOT gate, the state is going to look like 0. Nothing happens to the second qubit if the first qubit is 0. Minus 1, 1 over under root 2. This is another example of a Bell state, perfectly entangled. It will give the same measurement outcomes as the experiment over there. I can also have a state like this, 0, 1, plus 1, 0. I can create this state. How can I create this state? I can just put in a NOT gate over here. Instead of this NOT gate, I can put a NOT gate over here. I perform the calculation, I will get this state. This is also entangled. Perfectly entangled. And if I repeat this experiment, this state, and I do this kind of measurement, I will get a perfect anticorrelation. Whenever a 0 comes here, a 1 comes here. Whenever a 1 comes here, a 0 comes here. It's still perfectly correlated, anticorrelated nevertheless, but this is a perfect correlation which cannot be described by any classical physics. If I don't have superpositions, if I don't have the quantum world, I cannot have entanglement. And this is entanglement that makes quantum computing interesting. Yes? This state? How? What's the state of the first qubit? ये आपको शायद यहाँ से नजर ये 0 है. So can you factorize this into the first qubit brackets with the second qubit? No. Let me describe this. Now it's extremely significant in a full-fledged example which is called quantum teleportation. Alright, let me finish please. Acha. So, the quantum teleportation is going to sum up all the concepts that I've been talking about. Now, quantum information is actually extremely problematic. Suppose I have a state 0 plus 1 under root 2, and I have the state 0 just 0, and I have a qubit, and I have a measurement device with two output channels 0 and 1. Now I have to go somewhat faster here, so please catch up with me. And this quantum state here is unknown. It's either this state or this state. And I just have one copy of the particle. Now, the question is, if this detector fires, if I get a click on this detector, can I tell what's the state, what's the quantum state? Just have one particle, I cannot tell what the quantum state is. Okay? Because this state will give me this output always. This state will give me this output 50% of the time. So if I just have one copy and I just get this detector to fire, I cannot say what state the particle is. I can have some probability estimate, I can be somewhat confident, less confident, more confident, but I cannot for absolute determination, I cannot distinguish between these states. And if I also allow the possibility that the state could be ket 1, in a single measurement I can never distinguish what the state is. I cannot measure the state. So I will need multiple copies. But photocopying of quantum states is not allowed. I cannot clone quantum states. I cannot have a photocopy that takes a quantum state and makes multiple copies out of it. This is called the no cloning theorem. I cannot make copies of the state, which also is tied up with the fact that I cannot measure quantum states with absolute definiteness. Now, what quantum teleportation does is, I'm sorry if I answer your question, I won't be able to finish, I'll take questions at the end. What quantum teleportation does, the science fiction picture is that a particle is just transferred from one spatial location to another location. But quantum teleportation, now you've studied enough quantum mechanics or quantum computing, that it really means I would like to transfer the quantum state of one particle to a spatially separate, distant location with perfect fidelity. Perfect fidelity means without any errors. And I destroy the particle, the state of the particle at the first location, and an exact replica appears at the second location. But I have to destroy the state of the first particle. Now, how do I achieve that? Now, let me build a proper quantum circuit that actually does this. Okay, now you have to follow this. This is going to be a big diagram. I have 3 qubits. The third qubit is in an unknown state that I want to teleport. I want to move this state to another remote location. Okay. By the way, quantum teleportation is now done all the time. There are commercial devices, commercial systems and applications of teleportation. So this is one commercial aspect of quantum computing. I would like to teleport this state. Okay? I want to create a replica of this state at some other location. Because in quantum mechanics, it's a state that matters. If you are a different person, but if my state goes into you, you will be me. Because the state is everything. Okay? Amir Khusro also said, Tu man shudi, man tu shudam, tu man shudi, man tan shudam, tu jan shudi. Kakas ni goet bagadi man digaram, tu digri. So I am you am I am the body, you are the soul. So that we can't say that we are two different beings, they are the same thing. So entanglement is actually this unison. Now I want to teleport this state. And what I need to do, I need to have the first 2 qubits in an entangled state. Okay? So that's the key. I need entanglement for teleportation. So I create a pair of qubits that are entangled. So I would like to write down the state over here. Let's call this location 1. I don't want to clutter my diagram, so I write the states here. Psi at location 1, my state is, so this is an entangled state, so I can't write the state to the first qubit and the second qubit. So that's why I put these braces. I cannot separate out my description of the state. So my state is 1 over under root 2, say 0, 0, plus 1, 1. For the first 2 qubits, is this entangled? Yes. Yes, this is one example of entangled state. And the third qubit is in an unknown state. Unknown. So unknown means I actually don't know these coefficients, right? Alpha and beta. This is an unknown state. Any state can be written as a decomposition of the basis states 0 and 1. And all the information of the state is provided in these probability amplitudes. So this is an unknown state. Alpha and beta are completely unknown. I would like to transfer this information of alpha and beta to a remote location with 100% fidelity. Now what I would like to do, so I can write this state in the following fashion. 1 over under root 2. Alpha is just a constant. 0, 0, 0. First qubit, second qubit, is third qubit. Is this state separable? The first and second qubits are separable from the third qubit. But the first and second qubits are entangled amongst themselves. Plus beta 1, 1, 1. Alpha and beta are totally unknown. They carry all the information about the state. Now what I would like to do is yes. So I'm inputting the state 0, 0 plus 1, 1 on the first two qubits. Okay, I'm giving that. So these two qubits are in an entangled state. Alright? This is the third qubit, which is in an unknown state. I would like to transfer information about this state to a remote location. Yeah, so, alright. So then, but this is the most general scenario. Okay? So it will work if alpha is 0, beta is equal to 1. But first of all, I have to transfer both alpha and beta to a remote state. Why isn't there a possibility for? Alright, I don't understand your question fully, but I think I do. So these are the first two qubits. I prepared these qubits in an entangled state. Alright? Now, the third qubit is a totally unknown state. Alpha 0 plus beta 1. You could have written alpha 1 plus beta 0. Doesn't matter. There is some coefficient with ket 0 which is unknown, and there is some coefficient with ket 1, it's unknown. So this is completely general. And what's the question?
My question is, let's pretend that we have only one, we have a state where beta is 1 and alpha is 0.
Alright. Then this thing will not exist. If this is 0, then this thing will not exist.
Yes, but why can't that be beta 1, 0, 0?
Beta?
Beta ket 1, ket 0, ket 0. Why can't this exist?
So I'm just factorizing out. So this is the third qubit, the first two qubits. Do you agree with the first line?
Yeah.
I'm just writing this out. I'm just opening these brackets and writing this out as 0, 0 with an alpha, 0, 0, 1 with a 1, Oh, okay, alright, okay, sorry, I'm so sorry. I'm so sorry about this. So sorry. So 0, 0, 0 plus 0, 0. So there's a beta 0, 0, 1. Okay, plus alpha 1, 1, 0 plus beta 1, 1, 1. I'm so sorry. So there was something going in my mind. I knew something was wrong, but I couldn't figure it out. So when I multiply, or I'm not actually multiplying, I can write this state in this form, right? This along with this alpha, this along with this beta, and so on. Now what I would like to do is this second qubit and the third qubit, what I would like to do, I would like to perform a control knot on the second qubit and the third qubit. Okay? Now I would like to, nothing happens to the first qubit. In fact, the first qubit is carried by Alice. And she moves, takes her qubit, which is one part of the entangled pair, and moves to a far off planet. Okay? And Bob has one copy of the entangled pair and the unknown qubit, and he performs this operation, the controlled NOT gate operation. Now we would like to find out what's the state in this location, or in this part of the sequence. The state is going to be, so the third qubit is inverted if the second qubit is 1. So let's look here. I have alpha 0, 0. Nothing happens to the first qubit, nothing happens to the second qubit. Third qubit is inverted if the second is 1. Agreed? Nothing happens here. This qubit is inverted because the second qubit is in a state 1. Nothing happens to the second qubit. First qubit always passes unscathed. The third qubit, this is inverted if this is 1. So this is the action of the controlled NOT gate. Now what I would like to do is, I would like to perform a Hadamard gate here. Alright, now I need to manipulate this a little bit. So this is at location 2. I want to perform a Hadamard gate on the second qubit. Okay? So I'll just take this second qubit, this one, this one, this one, and perform a Hadamard gate on the second qubit. Okay? So what I'm trying to do now is simple, it's nothing complicated. I just take the state here and write this state in another fashion. I would like to write this in the following fashion. Alpha at 0, So I take the terms in which first qubit is in 0, alpha 0 0 plus beta 0 1 plus first qubit in the state 1 alpha 1 1 plus beta 1 0. Now I perform a Hadamard gate on the second qubit. I get psi at location 3. Okay? So now I'm here. Hadamard gate on the second qubit only, nothing happens to the first or the second. So nothing happens to this qubit alpha. Now this 0 goes into a superposition. 0 plus 1 under root 2 0 plus beta. This goes into superposition Let me actually simplify this a bit further. Let me write this in a simpler fashion. 0 0 second qubit, third qubit alpha 0 plus beta 1, right? So I'm taking this 0 as common. I'm factorizing out this state 0 from the second and third plus 1. This 1 is factored out and I get alpha 1 plus beta 0. Then I get this ket 1 on the first qubit, ket 1 alpha 1 plus beta 0. Alright? Now these alphas and betas can take a free ride. They can move with any qubit whatsoever. Alright, so this is my state. So this is the state. So what I've done over here, I've just taken this ket 0 as common. This is common. The second and third is 0 plus 1 with alpha and beta. Here I've taken 1 as common, 1 alpha 1 plus beta 0. एक मिनट मुझे let me see 0 0 1 alpha all right. जिधर मर्जी लिख दें. All right, fine. Now we would like to do a Hadamard gate on the second qubit. I get psi at location 3. Now this is the second qubit, right? If I do a Hadamard gate over here, this goes to 0 plus 1 under root 2. This thing I'm just reproducing. Alpha 0 plus beta 1 under root 2 plus 1. Now this state, I apply a Hadamard gate, goes to 0 minus 1 under root 2. This state on the third qubit is alpha 1 plus beta 0 under root 2. Now what I could do, I would like to just write these out, expand these terms. Okay, so my life gets a bit easier. I think it's a long path, but the results are going to be quite fascinating. Don't have much time right now. So I would just like to take that state, side application 3, and I would like to expand all of these terms. 1 over 2 is just a common. So this is 0, 0, 0, 0, 0, 1, 0, 1. Could you please speak out the terms? Zero, alpha, 0. So instead of writing 3 cats, I'm putting 1 cat just for convenience. 0, 0, 0 plus coefficient will find beta 0, 0, 1 plus 0, 0, 1 again plus alpha 1, 0, 1 again minus alpha G beta Alright, so this is the state at this particular location. Alright. Please, just 5 minutes. The result is going to be astounding. So what Bob is going to do? Bob, who has possession of 1 qubit in the entangled pair and the unknown state, he is going to perform a measurement. So this measurement will be either 0 or 1. This measurement will be either 0 or 1. Okay? So each qubit could be in state 0 or 1. This could be 0 or 1. This could be 0 or 1. So now let's try to look at this state over here. If I look at the second and the third qubit, there's a 0, 0 here and a 0, 0 here. So I would like to factorize the second and the third qubit together. I would like to put these terms together. If I put these terms together, the first, so I put 0, 0 for the second and the third qubits. The first qubit is in the state alpha 0 plus beta 1. Now I take 0, 1. I take this term and I take this term over here. The second and third qubits are in the state 0, 1. So I factorize the state of the second and the third qubit 0, 1. And the first qubit is now in a state beta 0 plus alpha 1. Now I look at the second and the third qubit and I choose 1, 0 here and I choose 1, 0 here. So now the second and third qubit is in the state 1, 0, whereas corresponding to this, the first qubit is in a state alpha 0 minus beta 1. Now I look at the last possibility that the second and third qubit is in the state 1, 1. So I look at this term and I look at this term. And my first qubit corresponding to these terms is beta 0 minus alpha 1. Now this is astoundingly beautiful because what happens here is Bob makes a measurement on these qubits. When he makes a measurement on these qubits, he'll get 4 possibilities. What are those possibilities? 0, 0, which means 0 here, 0 here. The second possibility is 0, 1. 0 on the first qubit, on his first qubit, which is the second qubit overall, 1 here.
1, 0.
The third possibility is that he measures 1 here, 0 here. The fourth possibility is that he measures 1 here, 1 here. Now he performs a measurement classically and he collapses 2 qubits. He just destroys 2 qubits in the process. But he gets 4 results. Either this, or this, or this, or this, with equal probability, by the way, because of this factor over here. The probability of each one of these collapses is 1 by 2 square, which is 1/4. So 25% probability is that this happens, 25% probability this happens, 25%, 25%. Now he gets 2 bits. These are 2 bits, not qubits, 2 bits. Right? 0, 0, 0, 1, 1, 0, 1, 1. And 4 possibilities. Now what he does, he writes this, his outcome, on a piece of paper. Say he writes 0, 1. And he transmits this information to Alice over a phone call, fax machine, email, through some classical channel. Now Alice has her particle. Her particle is this particle here. This, or this, or this, or this. And they have decided that if my result is 0, 0, then Alice will have a perfect copy of this state, right? The first qubit is alpha 0 plus beta 1, which is the state we started off with. So they have decided, they have met in the past, sometime had lunch together and decided that if my output is 0, 0, then your qubit is going to be an exact replica of the qubit that I'm going to destroy. But you'll get an exact replica. If my output is 0, 1, then you'll have to apply a NOT gate to your qubit. If Alice applies a NOT gate to her qubit, this becomes alpha 0 plus beta 1. It becomes an exact copy of her state. If Bob measures 1, 0, they've decided that Alice has to do another kind of gate, which is called a Z gate, which just inverts this sign. If Bob gets 1, 1, they've decided that they'll do a Z gate followed by a NOT gate. So, Alice chooses out of 4 possibilities. She does nothing. If this is Bob's output, she does nothing. If this is Bob's output, she does a NOT gate on her qubit. If this is Bob's output, she does a Z gate. If this is Bob's output, she does a Z gate followed by a NOT gate. And this qubit will be an exact replica of the unknown state. Thank you very much.